Greetings monkey brains. Today what I'm going to talk about is a phenomena which you may or may not have heard about, and that is that if I have two coils which are made to resonate together, for example the primary and secondary of a Tesla coil, that when I put the two coils close together the resonant frequency actually changes. Now how strong is this effect and under what circumstances does it occur? Let's tune our coils together to find out. Now my resonator is ready. My primary winding has several taps if I need them, and I have the two outputs from my secondary winding. Usually I put some foam inside to stabilize the two coils, but it's not necessary. Now we have to tune our two coils together. We do this by connecting different capacitors until we get the same resonant frequencies. Let's start with the secondary winding. I use a 16 nanofarad capacitor and connect it in parallel using a connector block. Be careful when choosing a capacitor. If you choose a capacitor between 1 and 50 nanofarads and your secondary has significant turns, it could develop a large voltage and destroy the capacitor. Make sure the capacitor has a significant voltage rating. If you use a capacitor, for example, above 100 nanofarads, this will bring the voltage down on the secondary, but also the resonant frequency. To find the resonant frequency of the secondary, you have to measure either the current or the voltage. To measure the current, you need a current probe like this. I showed how to make this current probe in a previous video, which I'll link above and below. To measure the voltage, you have to connect your probe across the capacitor, but be careful because of the high voltage. Now if you're trying to measure a Tesla coil and you want to put a top load as a capacitor instead of a normal capacitor, then you would measure the current at the ground point. Actually, I made a previous video about how to tune Tesla coils, which I'll link above and below. Now I need a driver. For this I'll be using my half bridge driver from a different project. The half bridge or full bridge drivers are best for this type of thing. However, you can use, for example, a push-pull or a single switch, but they may introduce other frequencies into the mix. I connect a crocodile clip to the center tap just so I can use the whole winding. Then I connect my half bridge directly to the primary winding without any capacitors, because I don't want any resonances in the primary interfering with the secondary winding. Then I connect the red probe to measure the current in the secondary and the blue probe to the gate of one of the MOSFETs just to trigger the scope. Once I'm fully set up, I switch on the power and then I tune the frequency of my oscillator until the current in the secondary becomes maximum, and that's the resonant frequency. Notice the input power becomes maximum at the resonant frequency, and this is why we start with a low input voltage. Then I use the cursors on the scope to find the frequency between two peaks, and it's about 29 kilohertz. Now to measure the resonant frequency of my primary, I have to make sure the secondary is completely disconnected so it doesn't interfere. I connect the yellow probe to measure the current in the primary. Then I connect different capacitors in series with the primary until I get the resonant frequency to be the same as the secondary, which was 29 kilohertz. So for me, I managed to achieve 29 kilohertz using a 100 nanofarad capacitor plus a 90 nanofarad capacitor. So now we've tuned both coils to the same resonant frequency of 29 kilohertz, we're ready to put them together and see what happens. So now I've reconnected everything. I have my 12 nanofarad capacitor on my secondary winding and a 190 nanofarad capacitor in series with my primary. My red probe is measuring the current in the secondary and the yellow probe is measuring the current in the primary. I turn on the power and begin to scan the frequency from low to high. Let's see what happens. So I find this resonance and measure the resonant frequency using the cursors, and I find out that it is 24.75 kilohertz, which is much lower than the 29 kilohertz we originally designed for. Notice here that the current in the secondary, the red, and the current in the primary, the yellow, are in phase. So I continue scanning upwards in frequency just to check for higher modes, and lo and behold I find another resonance. This time it's sitting at 35.71 kilohertz, much higher than the 29 kilohertz we originally designed for. This time the currents in the primary and the secondary are out of phase. So what is actually going on here? This phenomena is called frequency mode splitting. That is that when you have two resonators of the same resonant frequency and you bring them close together so that they are strongly coupled, then the resonant frequency actually splits into two modes, a higher one and a lower mode. The lower mode is the normal mode where the currents and fields are in phase, and the higher mode, so-called anti-mode, is where the fields and currents are out of phase. This can be understood by using the mechanical analogy of a coupled pendulum. Not to be confused with the double pendulum, the coupled pendulum has two modes. The first mode is where the pendulums oscillate in phase, and the second mode is where the pendulums oscillate out of phase. When two coils are coupled together, the magnetic field lines have a chance to loop around both coils at the same time. These magnetic fields contribute to something we call mutual inductance. In this case, the magnetic field lines cover a much greater area than would otherwise be the case if the coils were on their own, and because of that the mutual inductance is much greater, and therefore the resonant frequency is lower, resulting in that low frequency mode. In the case of the high frequency mode, the mutual inductance field lines can't make it around both coils because the fields from the individual coils are opposed, which leaves us with only the field lines from the individual coils, which are actually squashed in space because of the proximity of the other coils. And it's this squashing of the field line in space which leads to a reduced inductance and therefore the higher frequency mode. Now this leads us to an extremely important point, and that is that electrical engineers and physicists are used to thinking that the inductance is fixed. In other words, it only depends on the geometry of the coil, its diameter, the length, the number of turns, and any core material which is there. But actually, in our case, we don't have any core material, we haven't changed the number of turns or the geometry of any of the coils, and yet we have a higher frequency mode. And because there is a higher frequency mode, it means that the inductance of the total system must have somehow changed, and that shows us that the inductance is actually determined by the distribution of the magnetic fields in space, because that's the only thing which has changed between the two modes. Well, there's a lot more that we could talk about to do with this, but I just wanted to give a brief overview and explanation. I hope you enjoyed the video. If you want to help the channel, please like and subscribe. See you later.